treasure hunt real-time targeting of the long tail using training time markers. And training time markers are interchangeable with treasure markers, which in the context of this paper are things which are included within a special tag at the end of a prompt, which help a model give certain characteristics. So if you look at this graph, which shows the train distribution, which is skewed to lower token sequences, which means that when you count the number of tokens in the sequence that you're training upon, many of them are short compared to being longer. So this would naturally skew the responses to be shorter. But what we can see in the paper is that as you specify the length to be either concise, medium, or long, you still get a nice consistent distribution over, in this case, concise, medium, and long tokens. So this is essentially the goal of the paper, is to get desired behavior despite skews that exist in the training data. And the three contributions that are made are firstly to introduce a more general framework for controllability. We'll see exactly how the prompting is done in a bit. Also have long tail lifts, which means that data which is in a lower representation, so like anything that's not code, for example, still gets good evaluation. And then lastly, modeling underlying relationships. So what does this mean? In the context of this paper, they have a reduction in length violation from 36.58 to 0.75% in length constraint instruction following. What is length constraint instruction following? And it means like if you tell the model to have an output that is less than 200 tokens, will it actually listen or not? So when you just ask a model just in the prompt, in plain text, to have a prompt, for example, or an output that's less than 200 tokens, you can see that it has this equality of 36% being violations and the rest being conforming. Whereas when you actually enforce this with the treasure markers, you get a 0.75% violation rate, or more aptly put, a 99.25% correction rate. So when you look at the methodology, it's a standard token sampling regime where we have our output sequence Y given the instruction X and any training markers, which is modeled here by P of YI given XM and all of the previous tokens generated. And you can see here all of the tokens which can be added in this instruction set. So you have code type, you have language, which is at the very bottom. There are 23 languages in the that are supported, so French, English, etc. And then another one being length, which we've seen to be concise, medium, and long. And the token is appended to the prompt in this way. So you can have marker list, science, and French for domain and language, and then it's pre-appended to the output. So it comes to the end of the prompt and the beginning of the output. And it's only always in the output, whereas in the input, it's sometimes missing. And this is because we want the model to not depend on the guidance always being there, because some users may not always add the marker list. So what this means in a more concrete way is that to avoid the model from being overly reliant on markers for completion, or even worse, learning to trivially replicate the markers, they employ a dropout strategy on the input. So when you have the standard negative log likelihood here of Y and the marker given the input, we may or may not input the markers, so that it's like the model needs to learn to essentially infer the markers if it doesn't have them. And what happens when they actually do the dropout? So they did an experiment with 0, 50, and 70% dropout. And 0% dropout means that there's no dropout. The model always gets instructions, which may sound good, but in practice, it means that it cannot generalize. And you can see that's why it has really bad performance when you have 0 dropout on the dataset level. And this means that you should not pick this. And in practice, they found that the 50% data level dropout is the default, since it strikes a good balance between learning and generalization. So this means that half of the samples that the model is trained on do have the instructions of science and French in this example, and the other 50% do not. So the model must infer that when it actually comes to generation. And then when I mentioned the contributions, we talked about long tail domains, and you can see that they do benefit from training markers more than anything that's like highly represented. So you can see here the representation in a data set. There's a lot of code, culture, tech, conf, it's greater than 5%, but then these ones that are less than 5%, they actually improve by 9% overall in the Arena Hard Auto data set, whereas the highly represented data is improving by 5.7%. So it's greater benefiting long tail stuff, which is good because you don't want the model to just be only good at code if you want to have general purpose compute. And then in this example, we can see that within a task, you also get good performance on those specific tasks which are less represented. So for coding, of course, generation is highly represented and translation and repair aren't. But when you look at the relative improvement, you can see that repair and translation actually get the best improvement overall as opposed to generation, which once again is within the contributions to the paper saying that we improve on those tasks which are less represented in the dataset. And you can see the difference between just regular prompting where you have choose 199 words or less, which would have the 37% violation rate, versus specifically giving the model the length of tokens, which will then have a much better, essentially, length constraint following. And then another interesting thing which was discussed in the paper is on-the-fly treasure markers. So what this means is that they use Command A, which is the frontier model from Cohere, to add a set of marker lists to a prompt that were generated by AI in order to improve a prompt that does not have any markers. And this was also shown, if you'd like to check the results, to improve overall generation, even if it was not added by a human. And then in conclusion, in this paper, markers were proposed to training data to map out potential treasures that can be retrieved at inference time, such as specific task configurations or quality characteristics. And with this flexibility, users are allowed to hunt treasures without having to tediously engineer prompts or give in-context learning few-shot examples to optimize performance. So that's kind of a high-level overview of the paper. I was also included in this appendix the experimental setup and evaluation if you'd like to see that, and the link to this presentation will be in the description. Thanks for watching.